So our problem is to take a virtual address, which is going to be 0 to 264 is the range, or we can say there's n bits here, right? The physical address, it doesn't have to be represented by the same number of bits. So we'll just let the number of bits in the physical address be m. We're going to do a similar thing to blocks in a cache, which is the lower bits. If your page size is 2 to the p, then we'll say that those lower p bits will just map directly to the physical address bits and really do the mapping based on this upper level part. Right, so what was a block offset in the cache terminology, that's going to be a virtual page offset at the level of pages. And then we have a virtual page number. We need to map a virtual page number down to a physical page number, while the virtual page offsets just get copied down. So here's our problem now, to map the virtual page number to a physical page number. And we do that with a page table, which, as a first approximation, is just a big array that maps every virtual page number to a physical page number. And in the processor, because it has to deal with these virtual addresses all the time, it needs to know where the page table is. So there's a special register that can only be set in privilege mode called the page table base register that will point to this page table. The value of that page table base register is specific to a process. So that's how we get different results for different processes. It's by swapping out the value of this page table when we switch processes. Meanwhile, this page table, like other caches, will have a bit associated with every entry to say whether that cache line is valid or not. If it's not valid, that means we've asked for some piece of memory that's not currently mapped to main memory. That might be because it's on disk instead of in main memory. In any case, we have a page fault and it will need to be resolved somehow. But if the line is valid, then that gives us a physical page number that we can combine with the physical page offset. If we use this simple strategy for a page table, it gives us a fully associative cache at the level of pages, because we can map any virtual page number to any physical page. On the other hand, the table size has to be 2 to the however many bits we have left over. And we've said page sizes are 4K, that's only 12 bits. So with a 48-bit address space, that means we have 36 bits in the virtual page number. And making a page table with a whole pointer worth of information for what was it, 36 bits, that's going to be way too big. It's like 500 gigabytes or something like that. So a more realistic strategy is called a multi-level page table. It's the same idea, but we just break up the virtual page number into smaller chunks. And the page table base register points to a table that deals with just the first chunk. And then once what we have in that first table is not the whole page number. Instead, we have a reference to some other level 2 table, which is indexed by the next chunk, and so on. The reason this helps is we have a sparse array representation effectively. We only have to allocate level 2 tables when they're actually meaningful at level 1. So if level 2 and all the tables after it for a particular entry in level 1 would just be empty, then we can represent that by an empty pointer. And similarly here, if this level 2 pointer would go on to level 3 tables and so on that are empty, we don't even need to allocate the level 3 tables. So by lazily allocating those tables, allocating only as needed, we end up with a sparse array representation that's much more compact than the naive flat one. In the case of x86-64, there are actually 4 levels, whereas in 32-bit x86, there were 2 levels.